We're Team Fortune Cookie. I'm Liu Yi, and we have David, Ziyi, and Mingtao in this team. This is our project on control of smart home appliances with BCIs. The automation of home electric device is a new trend for technology advancement. Right now, we have smart coffee machines that could start brewing with a verbal cue. We also have smart speakers that follow the user's verbal commands. For example, Amazon Alexa and Google Home are both able to control home appliances, such as turning on lights and changing home temperature with users' verbal instructions. Our team then begins to think about improving this interaction of giving commands. Instead of verbal cues, could there be a more natural, smooth, and easy way of interacting directly with home appliances? In this class, learning about the brain-computer interactions, especially EEG data interpretation, we're inspired to combine two newly emerged technology. What if we can directly control the home automation device with our brain signal? Have you ever got yourself into this situation? After an exhausting day, you crawl directly into your bed, then notice all the lights that you're too lazy to get up and turn off. Now, imagine if you could just think, turn off that light, and the light will be turned off immediately. Also, this mind control device might help our people with disabilities live more normal lives. With our version in mind, we decided to start experimenting on making home light switches into an automation device. And this is how we came to our current goal for the project, making a prototype that reads real-time EEG data to control light bulbs.
Then, let's move on talking about some related work that provided by our course, which supported our study. During class, we have learned that one of the main goals of BCI-based applications is to achieve maximum independence for the patients, despite any motor disability. People who suffer severe motor disabilities are often homebound, and for this reason, environmental control applications focus on the control of domestic devices such as TV, lights, and ambient temperatures. This paper introduced us a pilot study dealing with the integration of BCI technology into a domestic environment. In this study, 14 patients with severe motor disabilities tested a device that provided environmental control. As output device, the system allowed the use of a basic group of domestic appliances such as lights, TV, a motorized bed, a front door opener, and a telephone. This provides us motivation and confidence to design such system by ourselves.
And through our research, we found some related work that could support us using NeuroPi as our tools. First, attention and medication value are caused by low alpha and low beta brainwaves, which is exactly what NeuroSky used to measure our attention and meditation scores. And second, NeuroSky used monopolar EEG data in our study, measure people's fatigue state with a result comparable to sophisticated medical instrument. In other words, NeuroSky is useful as a sophisticated medical instrument.
Okay, David here. I'm going to talk about the methods. So, since our goal is to create a prototype to create a light switch, there are some key components that I want to introduce for the project. So one of them is the NeuroSky man-wave headset, and then we use Python code, including NeuroPi, and then my own Python program, and then we pass it to Arduino, and actually we use the XB as a wireless transfer, information transfer, and then pass that to the actually Arduino board code you can find on the GitHub. So first of all is that I want to introduce you to the new Python 3 version of the NeuroPi. The old NeuroPi is actually for package Python 2.7, and personally I think we need to have 3.6 for developers with newer environment to develop more BCI applications. For the actual implementation, you can find it on the next slide, which basically there's some stuff regarding changing the parentheses on the print statement, removing sys, because we do not need to force quit the program. We can actually change the thread, we can change how to find keys in the dictionary and so forth. Then we'll talk about my own program for the Python algorithm. It's actually pretty straightforward. So the first step is actually connecting Arduino to the NeuroSky headset. And then we were going to read the attention and meditation data from the subject. So if the subject attention is higher than a certain threshold that we set for X amount of iteration, which we set X as well, then we will pass 1 to Arduino. So 1 in our case means turning on the light, and then 0 means turning off the light. Then in the other case, if the subject's meditation is higher than a threshold for 1 X iterations, we will pass 0. But there's a question of how many iterations we want to set and what threshold value we want to use. Basically what we did is that we let the subject think about turning on the light for X amount of time, and then we're going to analyze the graph that we generated from Excel. As you can see, the threshold for attention is about 85. 85 for a lot of people is really hard to reach on their attention level, and then it's really hard for them to hold for 0.7 seconds, 1 iteration 0.1 second. So that's why we set the iteration number to be 7. And the same thing for the meditation. However, for meditation, it's really hard for a lot of people to meditate. So we set a lower threshold for meditation, which is 75, and we'll stick with the same iteration number. And then we pass the Python to Arduino with PySerial. It's basically a pre-built library which we can use. It's really convenient. And in the Arduino, basically we read each serial 1 byte at a time. As I've explained before, if the Arduino reads 0, then it will send XB signal, I guess, turning off the light to the Arduino board. And if it reads 1, it will send turn on the light. For the XP implementation, is actually more like a wireless wire. Basically what it does is connects to the computer to the Arduino wirelessly. Different XP has different kind of range, and for mine it's about 3-mile range, so technically you can turn your light on and off, I guess, from another apartment nearby. And for our own, I guess, schematic sketch, I actually copied it from Freezing, and as you can see the graph below. So as for the result of the prototype, it worked. 4 out of 8 people we're actually pretty proud of. As for the product code, you can find them on my GitHub, and for the demo, it's going to be shown below.
We successfully reached our current goal of creating a prototype that reads real-time EEG data to control light bulbs. Our team wants to move beyond and set a future goal as creating an EEG headset that controls binary home automation devices. For example, turning on and off devices or increasing or decreasing speaker volume. We need to work more upon achieving this future goal.
So what do we learn here? First, we have a understanding of the NeuroSky headset, and we learn how to extract data and how to use it. And secondly, we find out like significant different style between Python version can affect our code. And third, we learn how to use real-life application of the EEG recording. We learn how to use EEG data on controlling light bulb and other kinds of things. The last one, we learn how to run experiment with different subjects. We learn how to train them, use the gadget, and we learn how to gather data from it.
There's also some limitations to our current system. First of all, movement disruption and artifacts. There are some artifacts such as eye blinks, attention distractions, and the movement of the head during the user testing period influence the user control over the light. Second of all, the user could also be influenced by what he or she thinks the expected conclusion are, and no experience confirmation bias. Also, there's a need to test our program on disabled subjects. Thirdly, there are also some limitation data using NeuroSky headset, because NeuroSky only has 1 electrode. The data we can collect is very limited. Next, the pre-built-in algorithm for real-time EEG source. We use the pre-built algorithm which provides us with the attention level that we need. To allow better control of the device and better classification, the pre-built algorithm may not be enough for the next approach. Next, limited control appliance. The number of controlled appliances is very low. We only applied the application of such system on turning on and off the light. Lastly, on the unreliable performance of NeuroSky. Sometimes the performance of NeuroSky is not very reliable and we have to test multiple times.
So for our improvement, we probably use headset with more electrode so that we can get more data, and also we maybe implement better algorithm to process real-time EEG signal. And as you can see, ORICA combined with the ASR serve as a great tool for filtering real-time EEG data. ORICA, which is online recursive ICA, is highly effective by the large amplitude artifact and therefore hard to use. And we can use ASR to remove that large artifact before we use ORSAA, and then use a real-time IC classifier, for example, iCatch, to remove the artifact-related ICs, and therefore we can get a filtering real-time EEG data and use it as in the study. And here's the data for the EEG. As you can see, the blue one is the original data, and it's kind of messy. And after the filtering, the red one seems more concentrated and more clear, and much more easier to use.
The second improvement was inspired by the experiments designed by Professor Desa. As Kronek stated in his paper, an increasing number of mental tasks from 2 only produce a very limited improvement in terms of information transfer rate. The experiment designed by our professor allows a new paradigm of this satisfaction and satisfaction system to work naturally with a 2 left or right class system. In this paper, she restricted analysis to a binary cursor control task, which could be applied to our binary light control system. The results of her experiment shows that the integration of 2 systems is promising, and it is also possible for us to improve our classification method using such new system to improve the information transfer rate. There are also some other improvements that we can done to our current device. The first is to test our project with disabled users and see the result. Second is to have a program that adapts to more people, because currently we can only work our program on a limited of user. The thirdly is to use a neural training pipeline to train the subjects to control the light more effectively. For example, to train them how to mentally concentrate or meditate.
For the future, we're hoping the interaction of smart home appliances with BCIs will be more smooth and natural interaction with very minimal latency issues and also a more comfortable headset. For now, Samsung has started on a new project on the first smart TV that can be controlled with dots. We might expect in the near future our home is going to be filled with mind-controlled home appliances that make everyone's life much easier.